Hey everyone, and welcome to this crash course on MoveIt 2 with ROS 2. You have learned ROS 2 basics and you want to work with robotic arms. Maybe you've already started to look at MoveIt 2, but you feel completely lost. Well, you have come to the right place. In this crash course, you will learn the basics of MoveIt 2 and see how to configure a robotic arm with MoveIt so you can make the robot move. So what are we going to do exactly? Well, first we will install MoveIt 2. I will then give you a URDF for a 6-axis robotic arm that we will use as a starting point. We will add collision tags inside the URDF and then create a configuration using the MoveIt Setup Assistant. I will show you all the steps you need to do. Once we have the configuration package, you will get an overview of the files that you can find in this package, and we will finish by starting the MoveIt demo so you can do some motion planning with the arm. To get started, you don't need to know anything about MoveIt, but you do need some ROS 2 basics, including how to write a URDF. So in case you are a complete beginner, I have other courses and tutorials that can help you first. To finish with this introduction, well, this crash course is great to get started, and if you want to go further, I have a much bigger course for you on MoveIt 2, which includes 7 hours of video content. In this full course, you will learn how to create the URDF from scratch, do the MoveIt configuration, and then also bridge MoveIt with your own ROS 2 application using the MoveIt C++ and Python API, and also you will see how to connect MoveIt to your own hardware using ROS 2 control. So if you're interested, you can find the full course link in the description below. Alright, and now let's get started with the crash course. To install MoveIt 2, it's going to be very easy. It's just going to be one line. So you can just go to Google again and just type install MoveIt 2. You will end up to this page here. So that's the MoveIt installation page with MoveIt 2 binary install. You choose your ROS 2 distribution. So if I'm using Jazzy, I go to ROS 2 Jazzy. If you're using another one, just pick the other one. And you can see that, well, we just need to run this command. Now, before we do that, you see that they recommend Cyclone DDS as a middleware. So ROS 2 is based on DDS for the communication, and the default one is called Fast DDS as for now. So it could work fine with Fast DDS, but there has been some issues and Cyclone DDS seems to work better, so we can actually change the DDS configuration for ROS 2. And to do that, we don't need to do anything complex. Okay, we just need to install the DDS and then to add one environment variable here to export one here in the terminal. So you can copy, well, here's not very clear, but you can copy the first command sudo apt install with ROS distro rmw cyclone DDS cpp. Just that. And we are going to put this in the terminal here. So I'm going to bring this back here. Okay. And install that. All right, I've already installed before. And then to actually use this DDS, you need to do this export RMW implementation with RMW Cyclone DDS CPP. And then it's going to use Cyclone DDS. And to be able to use it every time, I'm just going to add this line into the bash rc. So I'm already in my home directory, bash rc. And I'm going to add that actually at the beginning, well, at the end of the bash rc, but before the lines to source ROS 2, just like that. So now we have 3 lines. The first one to change the DDS to Cyclone DDS, then we source ROS 2 installation, and then we source for the Colcon auto-completion. Let's save and let's exit. Great, and now we can install MoveIt. We just run this. It's very easy. ROS distribution, MoveIt. Okay, and for me, it's also already installed. Great, and now just open a new terminal, and then you have ROS 2 and MoveIt 2 installed and configured on your computer. So as you can see, installing MoveIt is really not that complicated. To be able to get started with the course, we need a URDF for the 6-axis robotic arm that we are going to work with. All right, because if you don't have that, well, you cannot work with MoveIt. And basically for most things you're going to do in ROS 2, for any robot, the URDF is going to be the stepping stone of your application. Without the URDF, you cannot do anything. And that's also the case for MoveIt. And so to keep things focused on MoveIt here, I'm not gonna write the URDF from scratch. So the URDF from scratch, we do this in the full course, but here I'm gonna give it to you directly, okay? So you can download this, there is the zip file called MoveIt 2 Crash Course Starting Code. You can download this, so the link is in the description. And we are going to extract, okay? And inside we have my robot description. So this is a package. We're going to start from that. And what I'm going to do now is actually to create a workspace, so a ROS2 workspace, so we can put this package and we can build it, source it, and there is a launch file that we can start already to visualize the URDF. Okay, so let's go back to the home directory. Actually, I'm going to do that from the terminal, and I'm going to create a ROS2_workspace folder in the home directory. Okay, I go inside and I create an SRC folder. Okay, so that's basically creating a ROS2 workspace. Then, still in this ROS2 workspace here, I'm going to build with colcon build. All right, and this is going to create a build, install, and log folders. Okay, so I just had the source and now I have those ones. Now you know that to be able to source this workspace, we need to do a source install setup.bash. And to make it more convenient, we are going to add this line into the bash RC so that every time we open the terminal, our workspace is going to be sourced. So let's do that quickly. Let's open with gedit, and I'm just going to the path of the bash RC. Okay, so you should already know that. I go here, and well, what I've done already, you see I have my Cyclone DDS here line. I have the line to source the global ROS2 installation. That's very important. I also have one line to have the colcon arc complete. And then I'm going to add one at the end, source, that's going to be, so ROS2 workspace install setup.bash. All right, so I source this bash script that I have just generated here from my workspace. I'm going to save this, close, okay. And now every time we open a terminal, our workspace is sourced. Now I'm going to go to the source folder and we have nothing for now. So what I'm going to do is from this MoveIt Crash Course starting code, I'm going to just take my robot description and I'm going to put it in the source folder of my workspace. Okay, just like that. So now you see when I have the package here, you can just use this package as it is. We are going to go back one step and do another colcon build. There's just one package, so I don't need to put the packages select. All right, so it's going quite fast. And then, well, you can open a new terminal or just source from here. And what I'm going to do is I'm going to start, there is a launch file. So ROS2 launch my robot description. Okay, that's the package. There is a launch file called display.launch.xml. You can find it with the auto completion. I'm going to start, and you see that we have this. So we have a joint state publisher GUI here, where you see joint 1 to 6. And on RVs, we see a 6-axis robotic arm. Okay, so that's the URDF for the 6-axis robotic arm with 6 joints. So you can experiment a bit. So there's the joint 1 here, and then we have the joint 2 that moves like that. Then the joint 3, okay, the joint 4, here there's a rotation here. The joint 5, okay, so you see everything is a rotation. And then the joint 6 is here. All right, so you can make the robot move already and just get used to it a bit. One thing you can see is that if I move one joint, everything else is moving, okay, because we have a relationship between each joint. Okay, each joint is basically the parent of the next one. Actually, not joint, but each link is the parent of the next link with the corresponding joint here. We can actually see that. I'm just going to open quickly. I'm going to do that here. I'm going to do ROS2 run TF2 tools with view frames. So we're going to listen to the TF for 5 seconds, and then it's going to print a TF3. Should be here. We have the PDF. All right. And you can see those are the links. Okay. So the base link is going to be this base here. You can also check that with the robot model. Okay. With the different links. And the base link is that one. Okay. So you can also check that here. Then we have the shoulder link, the arm, elbow, forearm, wrist, hand, and we also have a tool link at the end. Okay, so you can see the TF tree like this. And now that you have seen the overview, let's actually just check what's in the code. So to check what's in the code, I'm going to my ROS2 workspace in my source folder, and I have already installed Visual Studio Code. I'm going to do code dot from here. All right, and let's see what we have. So we have my robot description. You see, this is a standard package with package.xml, cmakelist.txt. What do we do here? We install 3 directories, so a launch one, an RViz one with an RViz config, and then the URDF one. What do we have in the URDF one? You see, that's going to be the main URDF file. You see, myrobot.urdf.zacro. Here we include the 2 other files. The first one is common properties. In this one, I just have material tags here, gray and blue. Okay, so that's how I have my colors here from those material tags. And then I have the arm.zacro, which here contains all of the links and all of the joints of the robot. Okay, so we have the base link. You see the shoulder link, the arm link, elbow, forearm, wrist, hand. Those are the 6 links, okay, the 6 physical parts of our robot. Actually, not 6, but 7 parts. And then we have 6 joints, so join 1 to 6 between all those 7 parts. And you might also wonder, well, what is this thing here? We have an empty link. That's a tool link. Okay, so I've added an extra tool link. And you see I have a joint, that's the hand tool joint, between the hand links. So the hand link is basically the last link of the robot, and this tool link. I'm going to show you here. So this is the robot like that, okay? And if I go to, maybe I can remove the links. If I go to, I just put the hand, where is this? The hand link. And then in the frames of TF, I'm going to put the hand link. Okay, you can see the hand link. Well, maybe I can actually put the links again and reduce the transparency here. Let's say 0.6. Okay, so the hand link is basically, you see the origin for the hand. Okay, and then we have the shape for the hand link. But then if you want to add tools later on your robot, you are not going to add the tools here. You are going to add the tools at the end of this. So that's why I have created a tool link. So if I put the tool link here, you see the tool link is here. So it's kind of a virtual link. Okay, there's nothing physical attached here. But then later on, if you add a gripper, it's going to be very easy because you just create a gripper in the URDF, and then you simply say that the tool link is the parent link for the gripper. Okay, so that's why I have an extra tool link. So in the end, we have what? We have 7 links plus 1, and then we have 6 joints plus 1 also for the tool link. All right, so you can check the URDF for more details, but that's basically what you need to know for now. And then, well, we have a RViz config. Okay, that's why when I start, I have the configuration that I had. And then we have a launch file. And in this launch file, you can see that's the one we have started. Okay, we first start the robot state publisher with the URDF. Okay, so we pass the URDF. So you see that's the stepping stone of any application. You start the robot state publisher with the URDF. Okay, so that's what we did. Then we have started here a kind of fake joint state publisher. That's the window we have here. And of course, we have started RViz with the configuration. And so make sure you correctly install this and make sure you can build the workspace and then see this on RViz. And that's going to be the starting point for this crash course. To be able to configure the robot for MoveIt, we need first a URDF, which is what we have already with the links and the joints. But in the links, we also need collision elements. For now, we only have visual elements. Okay, so here we are going to add the collision for each link. So we are going to go to our workspace. I'm going to open the workspace with Visual Studio Code. And we are going to go back to the URDF. So We have the main URDF file with the common properties and arm.zacro. We just need to work on this file. Now, as you can see, each link here for each physical part of the robot has only a visual element. But for MoveIt to be able to compute collisions, you need to provide a collision element as well. Now, how do we do that? Is actually very easy. I'm gonna just do the base link here. So you have the visual tag, and after the visual tag, but still inside the link, okay, so it must be separate from visual, but inside the link, we're gonna add collision tag. So I open and I close. And what do I put inside this collision tag? Well, I'm going to have a geometry and an origin. I'm not going to have a material. And so if you check the robot on RVs, well, the visual here is going to represent the rigid physical part of this base link. And so what would be the collision element? Well, the collision element is the same as the visual, okay, in this case. So I'm going to take the geometry and the origin. It's going to be the same thing. All right, and that's basically it for the base link. So the visual is a box, 40 centimeters by 40 by 10. The collision is also a box with the same size, and this box is going to be centered around the origin, so we also need to offset the origin. Same value as for the visual. Okay, I'm gonna save. And now there is a very important thing to know is, well, the visual is just used for you to visualize. It's not really used for anything in ROS. But then the collision is used to compute collisions, right? So the more complex the shape that you have here, the more complex the computation, which means that by default, what you should try to do is to simplify as much as possible the shape. It doesn't necessarily need to be the same here between the visual and the collision, okay? The collision shape can be simplified. What does it mean? Well, for a box, what's simpler than a box? Nothing. But then, for example, you have a cylinder here. Instead of using a cylinder, which is a more complex shape than a box, you could use a box instead for the collision, okay? So visual could be a cylinder and the collision could be a box. And then, well, that's for the basic shapes. But if you have a custom mesh, well, depends on the meshes. But let's say you have a base link also with custom STL file or a Collada file. Maybe if this is very close to a box, you can make some approximation and say that the collision is also a box, which is going to make computations much simpler. Another possibility is that you create a new STL file with less details, okay? Because the visual might be very detailed with lots of round angles and stuff like that, okay? And lots of small details, but you don't need all of that to compute the collision. So what you can do is you can export one very detailed STL file or Collada file for the visual, and then a simplified STL file for the collision. All right, so that's the principle for the collision element. For this example that we have here for this project, well, we are only using boxes and cylinders, so it's gonna be quite easy to do. And then how to visualize that? Well, I'm gonna come back here. I'm gonna do a call con build. I'm gonna source, and then I'm gonna launch ROS to launch my robot description display.launch.xml. So same thing, we have the robot, and how do we see the collision? You go on robot model, and you see you have visual enabled. So I'm gonna remove the visual, and I'm gonna enable the collision. And you can see now I have my box here. Okay, that's the collision for the base link. All right, so you can toggle between visual and collision to see either the visual or to see the collision. So let's go ahead. We already have the base link. We're gonna do the shoulder link. So after visual and inside the link, we're gonna add collision like this. Collision. And actually what I can do is I'm just gonna add this for each link. So for the arm link after the visual, for the elbow link, for the forearm link, and then for the wrist link, for the hand link, And finally, we have the tool link, but you see the tool link doesn't have any visual. It's kind of a virtual link, so we don't add any collision as well, okay? So we will have 6 collisions in total. And then let's fill those tags. So in the shoulder link, you see we have a cylinder. Cylinder is already quite basic shape, so we could just keep the same. But for the sake of this example here, I'm gonna simplify as much as possible. So I'm gonna use a box instead of a cylinder, okay? So I'm gonna take the geometry here and the origin. I'm gonna put it inside the collision. And then instead of using cylinder, I'm gonna use box with size. So size here and then 3 dimensions. So what are the 3 dimensions? Well, the length of the cylinder is going to correspond to the height of the box, okay? So we will have the X, Y, and then the Z is going to be 0.5, okay? Because the cylinder is pointing up, so this is the height. And then what is the X and Y? So what is the size of the box? Well, we have a radius of 0.1, meaning that if we think of diameter, the diameter would be 0.2. Okay, so 20 centimeter on the X and the Y axis. So that's going to be 0.2, 0.2, 0.5. And then the origin, so the box is going to be centered on its origin. We need to shift by half of the height, which is 0.25. We can save. I'm just going to look at this one before doing the following ones. So let's do a colcon. So we are in the ROS2 workspace at the colcon build. You can also put those 2 ampersands and do source install setup.bash. So it's only one line and you do a build and the source. And then if I come back to the display launch file, I'm gonna remove the visual and enable the collisions. And you see now this is a box. So if you were wrong with the dimensions, you will easily see that in Arvis. Okay, so I encourage you to also check what you're doing. And you see that here. So the box is a bit bigger than the cylinder, of course, but it's simpler. And then the question is this going to be enough? Okay, do we need more precision? Because the collision is going to be more precise if we have a cylinder than if we have a box. But this is perfectly fine because anyway, you don't necessarily want the arm to go that close to this shoulder link. Okay, just think about it. When you walk yourself through a door, you just go somewhere in the middle, okay? You're never really trying to go as close as possible to the door without colliding to the door, okay? You always have some margin. So it's not a problem to have a bit of extra margin when calculating the collisions. Unless you really need a high precision, then it's completely fine, okay? So here you can see for all the cylinders, we can use boxes, which is not gonna make a big difference. Okay, so let's go back to, I'm gonna stop this and let's go back to the code and let's continue. Okay, so for the arm link, we are going to also take the geometry and the origin, put it inside the collision. This is a cylinder, so I'm gonna use a box instead. Box, size, and then the radius is 0.05, so diameter is gonna be 0.1, 0.1, and then 0.6 for the length, which is the height of the box. Okay, so that's same logic here. And then the origin also is shifted by 0.3 because by default, the shape is gonna be centered around the origin. So we need to add half of the height. Okay, so you see, we can go quite quick here. I'm gonna do the same for the elbow. So I'm taking the geometry and the origin. I'm gonna replace this with a box. Size. Okay, so what is the radius? 0.05. So the diameter is 0.1, 0.1, and then the length here, 0.1. And the origin is correct. Let's go with the forearm link. We take geometry and origin. Same thing, we do box with size, which is 0.1. radius is 0.05, so the diameter is 0.1, and the length 0.5. I'm going to the wrist link, I'm taking the geometry and the origin. And this one, no need to change anything, it's a box, so we keep the box, same dimensions. And then for the hand, I'm just taking the same stuff, and this is a box, so we don't change it. Okay, so you see it goes very fast. I'm gonna save, and that should be it. Okay, so now we have a collision tag as well as a visual tag for each link. For the base link, the shoulder link, the arm link, the elbow link, the forearm, wrist, and hand links. I'm gonna go back and I'm gonna build in source again and run. Okay, you can check if you have any error log here. Okay, we don't have any, so it should be okay. And then I'm gonna remove the visual, enable the collision, and you see I have my full arm, okay, with only boxes here. And you can see I can make the robot move, okay. And so this is this is basically the same thing. It's just that this visual is gonna be used so that you can actually see what's happening. But then this collision is so those shapes are gonna be used actually by MoveIt to compute collisions. And you can see that some shapes are colliding. For example, here, the elbow is colliding with the arm, but this is okay. When two shapes are adjacent, we're gonna be able to disable the collision. So this is just like if there was no collision. But for example, if we have, let's say, something like that, okay, you see that we can do this. Okay, we can go inside the shoulder link. And so MoveIt is gonna make sure that this doesn't happen. And also if you have other things in the workspace, if you have other shapes, then MoveIt can also compute the collisions thanks to those collision elements here and the collision element of the other shapes that you have in the workspace. All right, and so that's basically it for the collisions. Now the URDF is complete and we can start to configure the robot with MoveIt. Now that we have a URDF with all the links and joints as well as collision tags inside the links, we can configure the robot for MoveIt. How do we do that? Well, first make sure that you have correctly installed MoveIt from the installation section, and you should be able to run this. So ROS2 launch, there's a package called MoveIt Setup Assistant. Okay, you can use the auto completion. And then it should be setupassistant.launch.py. Let's press enter and you should get this window here, the MoveIt Setup Assistant. And through that, we are going to configure everything and then it's going to create a new package for us. Okay, so do we want to create a new or editing and exiting package? We're going to click on create new configuration package. Now you need to load a URDF or Collada robot model. So what we are going to do is we're going to browse and we are going to go to ROS2 workspace, source, my robot description, URDF, and we're going to take myrobot.urdf.zacro. Click on open. And so you just give the path to the file in which you have the URDF. We click on load files. Okay. You see success, and you can see here you should be able to have, so it's kind of an RVS view, you should be able to see the robot. We have the visual and we have the collision. So you should be able to see this. If you see this, it means the URDF has been successfully loaded. Okay, now we can go ahead and we're just gonna do everything step by step, okay, one by one. So self collisions. What I told you is that some collisions can be disabled. For example, between the shoulder link and the arm link, there's going to be a collision here that can be disabled because it's just adjacent. And then some collisions might never happen because just physically impossible. And so what we can do here is just one thing to do. We're going to click on generate collision matrix. And you can see that it's going to generate a matrix here with, for example, between arm and elbow, those are adjacent, so we disable the collision checking for that one. same as between the base and the shoulder. You see the elbow and the forearm. And then you have stuff like arm link and hand link, because MoveIt has computed that it's not possible for this to be in collision with that. So we're just gonna disable the collision checking, okay? And so, well, you just need to click on that once and that's it. Then we're going to go to virtual joint. And you can see here, create a virtual joint between the base, robot link, and an external frame of reference. So it allows to place the robot in the world or on a mobile platform. And so the base link here, that's the root link. I'm gonna add a virtual joint and I'm gonna name it virtual joint, okay? The child is gonna be the base link, and then the parent, we're gonna write world. Okay, so basically we are creating a virtual link that name is world, and there's gonna be a transformation between the world and the base link. It's gonna be fixed, okay? So it's basically at the same point, but then it's gonna be helpful. For example, if you want to use some simulation tools, it's gonna allow you to have this robot attached to the world, okay, where you're gonna create the object and different robot. Okay, so I usually do this when I have a robotic arm. I often do this. I create a virtual joint from world to base link, and that's fixed. Okay, there's not much more to do. Just click on save, and we have our virtual joint. That's it. Then we're gonna go to planning groups. Okay, this one is very important. And the planning group here, well, we have a 6-axis robotic arm, so we have a group of 6 joints that we need to create. And so MoveIt is going to create motion planning for this group. We're gonna click on add group, and let's say we need to give a name. Let's say arm. Okay, that's an arm. We're gonna choose a kinematic solver, and you're gonna choose KDL kinematics plugin. All right, you can leave this as it is, so the default values. And then we don't need to worry about this, and we are going to add the components to the group. So we can click, for example, on add joints. And here, well, we're gonna start from, well, we only really have 6 joints to control, okay? But I'm also gonna add the 2 virtual joints that we have here. So I'm gonna click on this and then shift until the hand tool joint. I'm gonna select all of them and then click on this arrow to put them on the right side, okay? And then I do save. Okay, so you see I have an arm group with all those joints, and you see fixed, and then we have 6 revolute. The joint 6 was actually continuous, but here it's written revolute. It's okay. All right, and well, you see I have 1 planning group. Okay, that's very important. And now that we have created this planning group, maybe you can notice that here on the left, we had some steps that were disabled, but now everything is enabled. And so if I put the collision, you see, this is the collision, this is the visual. So the planning group, the arm is the whole thing, okay? When we will add a gripper later, we're gonna have 2 planning groups. For now, we just have 1. Then we go to robot poses. We can create some poses for the robots. This is quite convenient. We're gonna create some poses and give them a name. And so later it's gonna be easy to make some tests between different poses. So let's click on add pose. And well, everything to 0, I'm just gonna name it home, for example. You could define any home position with any joint position as you want. Here, I'm just gonna say that this is the home position. So I select the planning group arm, I say home, everything to 0, save. Then I'm gonna create, let's say, a new one. Let's call it pose _1. And well, let's just, for example, do this here. Let's just add a pose just like that. Okay, so that's gonna be the pose 1. I save, and then let's add another one. Let's call it pose 2. Okay, so I put some random values. It's okay, like that. Okay, maybe this one here, and then like this. Okay, it's just random poses. Okay, so I can make the robot move, saying I want to go to pose 1 or pose 2. I'm gonna save, Okay, so you see I have my pose. So the home pose, pose 1, and the pose 2. All right. So we can just save this. I will also show you later on how you can add directly some poses into the configuration file without having to do this here. Then we're gonna go to end effectors. And here, well, we don't have a gripper. So if you click on add end effector, you can see we could put a name and then an end effector group, but we don't have a group for the gripper yet. Okay, and parent link here, well, would be the tool link, and then you would have a group for the gripper, but we don't have that yet. I'm not gonna do it. Then I'm gonna go to passive joint. So if you have any passive joint that you don't want to control, so here we have 6 revolute joints, but if there is one that is passive, okay, you can add it here. We don't have passive joints. We don't have any, so we're just gonna go to the next one, ROS2 control URDF modifications. And so here, well, if you already know ROS2 control, then you will understand what this is about. But if you don't know, it's gonna be a bit of black magic. So ROS2 control is the bridge between the software, so between ROS2 and the hardware. And basically, when you use ROS2 with hardware, you will use ROS2 control. So I have a complete course on ROS2 control that you can check if you want. But here, the good thing about MoveIt with this MoveIt Setup Assistant is that it gives you already the ROS2 control configuration. You don't need to do much, actually. So that's quite a good news. And we're going to use ROS2 control, but we're not going to do that much. We're going to use what this package is giving us. And so we need to specify command interfaces and state interfaces for each joint. So how do we want to control the joint? Here we want a position control. Okay. If you wanted velocity control, you would put velocity. For example, if you are controlling a wheel, that would be a velocity control. Here it's a position control. And then the state interface, we're going to read what? We're going to read the position. And well, I'm gonna remove the velocity here. Okay, so we're gonna have position control and position feedback. I click on add interfaces, and you see that for each joint, so there's gonna be some additional tags in the URDF. You see for joint 1, we have a command interface position and a state interface position with also some initial values. All right, so basically you see we have this from joint 1 to joint 6. Okay, this is something you need to do for ROS2 control. I'm gonna come back to this a bit later. Okay, so you can just check position, click on add interfaces, and that's it. Then we go to ROS2 controllers. And well, actually for ROS2 control, we have what? We have the hardware interface with the command and the state interfaces, and then we have the controller. So the controller is gonna receive the command from MoveIt, it's gonna do some interpolation and stuff like that. And it's gonna send this command to the hardware through the hardware interface. Okay, so we have two things in ROS2 control, the controller part and the hardware interface part. Now for the controllers, well, you just need to click on this and that's it, okay? So it's gonna create an ARM controller with the type joint trajectory controller. And so this is basically what MoveIt is gonna send somewhere with a topic or actually an action. And then we have a controller that's going to be loaded automatically. It's going to handle everything. We're going to go also to MoveIt controllers and just click here. Okay, so it's going to create an ARM controller with the ROS2 controllers and the MoveIt controller. So this one is going to send the command to the ROS2 controller and it's going to also use the hardware interface. Okay, so once again, if you've never worked with ROS2 control, this is going to be a bit of black magic for you. But I'm going to come back to this a bit later, so with more details. Okay, so make sure you have all of that. And then we go to perception. If you have a 3D sensor with 3D perception and stuff like that, you could, for example, with point cloud or depth map, you could configure that here, but we don't have any. Okay, so we're gonna go to launch files and you can just keep all of them. Okay, we're gonna create all the launch files. We only really need the move group and the demo, but let's just keep all of them. It's not going to be an issue. Then you go to author information and you might be tempted to leave it empty, but if you leave it empty, I think you're going to get an error in the next step. So let's just put whatever. You can put to do if you want and email, to do, at todo.com. Okay, just make a valid email with the at and the dot something. You can put your name if you want, of course. And then we go to configuration files, and you're gonna need to check where you want to save this package. So we're gonna browse and let's go to source. Okay, let's click on OK. And actually no, not my robot description. We're gonna write here my robot MoveIt config. Okay, it's gonna create a my robot MoveIt config folder. That's actually gonna be a package, and in this package is gonna add all of those files. You see we have a package.xml, we have a cmeclist.txt, and then we have config folder with some stuff and a launch folder. Let's click on generate package. Okay, you may have some warnings. For example, no end effectors have been added. That's normal because we haven't added the gripper yet. Let's click on OK. And then you see configuration package generated successfully. If you don't have that, then make sure you fix all of the errors that you could have done in the previous step. And don't close the window, okay, for now, before you save the files, because if you close the window, you're gonna lose all your progress. Now what I'm gonna do is I'm gonna go back to my workspace, and you see I have now a new package, my robot MoveIt config, with everything, okay, with all the different files. And so once you have this, then you can, if you want, you can close, you can click on exit, for example, and exit the setup assistant. If you ever want to modify this through the setup assistant, you just start it again. And instead of creating a new MoveIt configuration package, you do edit existing, you browse. So you browse, you see you should, let's cancel, you should browse where you have the MoveIt configuration. So ROS to workspace, source, MoveIt config should be here. Let's load the files. Okay, and you see we have everything again here. Okay? So that's how you can come back to an existing MoveIt config. I'm gonna save, and you see that, are you sure to want to exit? Because if you do that, you're gonna lose all the new progress. Click on OK. All right, and we have the new MoveIt config package. You have already made a lot of progress. Congratulations. Now we are more than halfway through the crash course. I hope that you're learning a lot, and I also hope that you like the crash course. If you find it useful, then you might want to check out my bigger MoveIt 2 course, which contains more than 7 hours of structured video lessons, and which will take you much further into the understanding of MoveIt 2. In this course, you will also learn how to create the URDF from scratch, use the MoveIt Python and C++ API, and connect MoveIt to your hardware with ROS 2 control. Well, I will leave a link in the description if you're interested. All right, and let's continue with the video. We have used the MoveIt setup assistant, and now we have a new package. So actually, let's just go through this package and let's see what are the files that we have, okay? That's gonna be a quick overview. I'm not gonna go into details for everything, but you will know basically where to find the information and maybe how also to modify stuff without having to start the MoveIt assistant again. So first of all, we have the package.xml, okay? Probably don't need to do anything here. We have the cmeclist.txt, as you can see, which is installing the launch folder, for example, and the config folder, okay? So nothing really special here. And then we have config and launch folder. So let's go to config, and we have quite a lot of things. Let's go to the files one by one. So we have the initial positions.yaml. So if we are using the fake system, so you will see that with MoveIt, we can use the fake system. Basically, it's going to be a kind of a simulation, or we can use the real hardware or Gazebo or something else. But if we are just testing MoveIt with what they call the fake system, then those are going to be the initial positions for each joint. So here it's 0 everywhere. Then we have joint limits. Here, I'm going to come back to this, but we have a default scaling factor for the velocity and acceleration. So between 0 and 1, 0.1 means 10%, which means that by default, your robot is only going to go at 10% of the speed, of the maximum speed. Okay, it's just so that you can test, and if you test with real hardware, it can be a good idea to reduce the speed just in case the robot is doing some weird behavior. At least it's going to be slow and you can stop it on time. And then we have joint limits for each joint. I'm going to come back to this. Actually, we're going to fix that very soon. You can see, do we have velocity limits? Do we have acceleration limits? And then we have some values. So here it's in radian per second. Okay, so it's going to be 1 radian per second limit for each. You see for the joint 6, it's a bit different because we had a continuous joint where we're going to see that a bit later. Then we have kinematics with the kinematic solver, the KDL kinematics plugin. Okay, don't need to touch anything here. We have the MoveIt controllers. Okay, MoveIt simple controller manager with the arm controller and the type and the joint. Okay, this there's no need to do anything here. We have the RVs config for when we're gonna start the demo, so no need to do anything here. Then we have, you see, the ROS2 control tags for the URDF. So that's gonna be added to the URDF actually. Okay, so you see we have the hardware interfaces for each joint. Here, command interfaces position, state interfaces position with default values. And also we use here we use a mock component, okay, for simulation. All right, so this, I'm gonna also come back to this later when we use the real hardware. Then we have, and I would say this is probably the most important file, we have the myrobot.srdf. So this is yet a new extension, and this is gonna be the extension used for MoveIt. And here you can see we have the robot named myrobot. And then we have most of what we have defined in the MoveIt setup assistant. So we have defined a group named arm with all those joints. All right. So if you want to modify the group, you can also modify here directly, or you can add another group without having to go back to the assistant. And then we have defined some, you see, home, pose 1, pose 2 with those values. Okay. So once again, you can easily modify this if you want to add, remove, or modify some poses. You just do it here. All right. We have the virtual joint that we have created between the world and the base link. And then we have all of the disabled collision tags. Okay, that was the first step. Okay, with the adjacent, never in collision. Okay, so most of the information is here. And if you modify it and you build again, then this is going to be taken into account from this file. Let's continue. We have the Zacro file. So this actually is going to be the main URDF file used when you start the demo. And what it does, as you can see, it's going to include my robot URDF.zacro from the description package. So it's going to include our main URDF file, which contains the command properties and the arm with all the links and the joint. All right, and on top of that, it's going to add the ROS2 control configuration here. Okay? So the URDF file now is the robot that we had plus some ROS2 control tags. And then to finish, well, we don't need to worry about this one. And we have the ROS2 controllers. You see, this is used by ROS2 control with the update rate in Hertz. So that's 100 times per second. And we have a controller for the joint states. Okay, so we can publish the joint state and make the robot state publisher work correctly and publish the TF. And we also have the ARM controller, okay, which is going to receive the command from MoveIt and execute that command. Plus some configuration for the ARM controller with the name of the joints, everything. But you can see everything is already configured for you. All right. So to recap here, the most important file would be, I would say, the SRDF with most of what you've configured, and you can modify this. Then we have a URDF file that includes some ROS2 control configuration. We also have some ROS2 control parameters for the controllers and also MoveIt controllers. So this you don't really need to modify. And we also have stuff like the joint limits and the initial positions that you can modify as well. And then you need, of course, to build, source, and run again. So that's it for the config. In the launch, we have several launch files, but the two that are going to be interesting for us is the move group and the demo launch py. As you can see, it doesn't really contain the launch instructions here. It's a MoveIt configs builder stuff. Okay, you can see generate move group launch. This is going to go to another file and well, you can see that it's actually quite long. Okay, there's a lot of stuff. But what you need to know is just that the move group launch file is gonna start MoveIt. So when we actually create our own launch file and we want to start MoveIt from there, we're gonna need to include this launch file. And then what we're gonna do in the next video is we're gonna actually test this configuration package, and we're gonna start the demo.launch.py. And well, then you have the setup assistant that you could start to just modify this package directly. And then you have other launch files. You don't necessarily need them, but it's not a problem to generate them. So, well, they are just here. All right. And that's basically it for this quick overview. Let's now test this new MoveIt package that we have. So what we want to do here is from my robot MoveIt config, we want to start the demo.launch.py launch file. So that's what I'm going to do. First, we need to, of course, build the workspace. So we need to build this package. I'm going to just build everything. Okay, the description and the MoveIt config, and then source install setup.bash. Now you might think that, well, we have just generated a package and we have a demo launch file. It should work out of the box, right? And actually, it's not going to work. So we're going to start it. I'm going to show you the error, and we're going to fix the error so that we can actually run the demo launch file. And so let's do ROS to launch my robot MoveIt config and then demo launch py. So ROS is starting, and well, there is nothing here. And you see we have some errors. And if I can find the error, okay, so it's here. You see parameter, robot description planning, join limits, join one max velocity has invalid type, expected double got integer. Okay, so if I go back to actually the config and the join limits here, this should not be an integer number, it should be a float number. Then you might think, why does the MoveIt setup assistant just give you an integer here if then MoveIt expects a double number? And well, I don't have an answer for that. Maybe they thought that ROS was not complex enough, so that they added an extra level of complexity, so you have to debug even the demo launch file. And so what I'm gonna do is, well, I'm gonna put 1.0 everywhere here like that. Okay, and I'm also gonna put true for the joint 6 and 1.0. Okay, so 1 region per second for each joint. And I think that, well, just to be sure, I'm also gonna put the acceleration limit. Okay, so I'm gonna put true, oops, here, because it might lead to more errors. And I'm gonna put 1.0 as well for the acceleration limit. You can use those default values, and then you can put more or less depending on the robot that you have. I save, and that should be okay. All right, so just put everything to true, and you put a max velocity and max acceleration. That is a double number, not an integer. So we stop. I am going to build again, source and run, and there's gonna be something else to fix, but now it starts. Okay, so you see, what do we have in the logs? Lots of stuff. But you see we are configuring the fake system here. So that's the ROS2 control configuration, and then some more MoveIt stuff with the planning adapter and stuff like that. Okay, we are loading all of the move group functionalities. You see, you can start planning now. If you see, this is quite a good sign. And then we are loading the different controllers. So the ARM controller and the joint state broadcaster. And if you see this, well, it looks good. And ROS is here actually. And so you see, this is what we have. And maybe I can close that one. And on this ROS view, we have, you see, motion planning. And so what we can do is, Well, on the actually context, we have OMPL, okay. Planning, we're gonna select a planning group. Start state, I'm gonna say current state. And the goal state, you see here, for example, I can choose pause 1. So we want to go from here to there. Then I can do plan, and you see it is planning the motion here for the robot. So, and it's looping here, and you see successful. But then we can do execute to actually make the robot move. And this is where we're gonna have an error. So still moving because it's the path planning, but then you see we have an error because, well, the controller could not actually be found. And for this, well, I'm gonna give you the solution because it's hard to find. You could list controllers, you could list the actions that are running, so all the actions, the topics, and the controllers, and you will see that there is a problem with one of the namespaces. So I'm gonna go to MoveIt controllers, and in ARM controller here, we have type, joints, and then we can add another action NS, so inside ARM controller. So action namespace, that's gonna be follow underscore joint trajectory. All right, and there's one more argument I'm gonna put, so one more parameter, default true. Okay, so you just add this, that's a quick fix so that the demo can work. And then we can go back and let's do a build source and run again. This time, so I'm going to bring again here. I'm going to bring RVs and let's remove that as well. Let's do, so we have OMPL. We select the ARM current state and then let's say pause 1. We do plan. It works as before, and then we do execute, and you see that now it is working. So the arm here is moving. It's moving very slow because we are only at 10%. You see velocity scaling 10%. What you can do if you think that this is annoying to see the loop here for the planned path, you go to planned path and you can remove loop animation. Then we can increase the, let's say we increase the velocity scaling to 100% or less as you want. Let's say we want to go to pause 2. Okay, we're gonna do, so you can do plan and then execute, but you can also do plan and execute. So this is the planning and then this is the execution. All right. And then you can also, if you want, you can modify, you can move this here. Okay, and we can do here, plan and execute. Okay, so I encourage you to play a bit with this, okay, to get familiar with this and just try different combinations. There is one thing that we're gonna do also is to do a Cartesian path, because by default, well, MoveIt is gonna make the robot move and all the joints move, but if we think of the last point, I'm gonna call the end effector tool, so the tool point here is not necessarily gonna move in a linear way. Okay, it could be a round trajectory. If you want to move in a linear way, you're gonna use the Cartesian path. Know that if you use this, you're adding more constraints, and so MoveIt might not find a valid path. For example, from this, if I want to go to pause 1, I don't think it's gonna work if I put Cartesian path. You see, it's starting to plan, but from this point, we get to what's called a singularity and we cannot go further. Okay, so if you use the Cartesian path, you might be more limited. So if I remove the Cartesian path, now, you see it's gonna work. I am going to put here on the planned path, I'm gonna put the show trail. So you can put show trail, okay, to see the trail for the trajectory. And then what I can do also, if I go to links, maybe to link, show trail, okay, and let's just do a plan and execute. All right. And you could see the trail, but it disappeared. So actually, I'm gonna not go in the planned path, but I'm gonna go in the scene robot. And then scene robot, let's say tool link show trail. You can show the axis if you want. Let's go back to the pose 2. Let's do plan execute. And you can see now, okay, we can see more clearly. We have the trail for the tool link. So that can be quite useful, okay, to see where exactly the robot is going. And now let's say I'm going to use the Cartesian path. And I'm going to give a simple, I'm just going to go up a bit here. Okay, should work, should be fine. Let's do plan and execute. Okay, you see the robot has moved. And the robot has moved, you see the tool link has moved in a linear way. Then let's say, I don't know if I can go much. Okay, maybe like this. I do plan and execute. Okay. And you see now the trail is linear. Okay. If I didn't use the Cartesian path, maybe the motion plan would have been different and be a bit more like this, going up and down or like this. Okay. So this is an option we're going to come back to later. Okay. It's quite useful. And one thing to note is that with a 6-axis robotic arm, you can do Cartesian path for small distances. But if you want to do bigger ones, and if you want to do soldering, for example, then you might need a 7-axis robotic arm. So you're going to add one extra axis, one extra joint. That's going to create some redundancy. But thanks to this redundancy, it's going to improve the chances of success for the planning of the Cartesian path. All right, and that's the end of this MoveIt 2 crash course. I hope you could learn a lot and get a better understanding of how MoveIt works. So to recap, you started from a URDF describing a 6-axis robotic arm. You have added collision tags and then configured the robot with the MoveIt setup assistant. At the end, you could see the robot move on RVs and give different kinds of MoveIt commands. Now, you might wonder, how can you create the URDF from scratch and apply that to your own robot? Also, how can you connect a ROS2 application to this MoveIt package? And how to connect MoveIt to real hardware? Also, how to add an end effector tool like a gripper to the arm. Well, that's exactly what I cover in my full MoveIt 2 course, which contains 7 hours of video content, additional practice activities, and downloadable code templates that you can use for your own projects. If you're interested, you can find a link in the description. And if you like the way I teach, you will love this course. Here is actually an overview of what's inside the course. So here I am inside the course, and you can see we have 10 sections. Okay. In the first 2 sections, there's going to be introduction. You will get also more insights about what is MoveIt 2, so why do we need it? And then we're going to do a full installation with ROS2, MoveIt 2, and some additional tools. Then the section 3 is actually how to create the URDF for the 6-axis robotic arm. So the URDF that I gave to you at the beginning of this crash course, well, here we are going to do it from scratch. Okay, you will get a complete review of the process of how to actually write a URDF with links and joint, and then we are going to write the URDF together, also using Zacro. All right, so with this, you will be able to also use URDF for your own project. Then the section 4 is basically what we have done in this crash course, okay, to add the collision tags and to configure the robot for MoveIt, and also how to launch the demo launch file. Then you can see that we are adding a gripper to the arm. So we will add the gripper to the URDF. We will also configure the gripper with the MoveIt setup assistant. And you can see that in the end, we will have the gripper here, and we can also do some motion planning for the gripper. We can open the gripper and we can close it. After that, we're going to create a bringer package, so you can create your own launch file. Okay, so we won't need to start the demo launch file. You can create your own launch file for your own application. And then it's time to use the MoveIt API. So there's one section for the C++ API and one section for the Python API. Here you're going to learn how to do a joint pose, a goal pose, a Cartesian path. We are going to integrate the C++ API inside an object-oriented programming node. And we're going to end here with a complete template that you can use in your own applications to bridge, well, your ROS2 application to the MoveIt commands. All right, so that's the C++, the Python one. And finally, we also have a section on how to connect MoveIt to the hardware. So a quick ROS2 control recap, and then I'm gonna give you an hardware interface, and you're gonna see how to plug this hardware interface to your existing MoveIt configuration. All right, so there's much more in this course, and that's a really complete MoveIt course. So once again, you can find the link in the description. And thank you for watching. I hope to see you in the course.